A variational autoencoder (VAE). It is a generative model capable of learning a latent representation of input data. Unlike traditional autoencoders, VAs learn a probability distribution over the latent space, allowing for generation of new data points. A variational autoencoder (VAE). It is a type of generative model that learns to encode data into a latent space and then decode it back to reconstruct the input data. It differs from traditional autoencoders by learning a distribution over the latent space rather than a fixed encoding. Its key components are encoder, latent space, and decoder. The encoder maps input data to a latent space representation. The latent space. It is a lower dimensional space where data is represented as probability distribution. The decoder generates output data from the latent space representation. Let's discuss about an autoencoder first, a VA's predecessor. Imagine an autoencoder as a magical machine that learns to compress images into a hidden code and then rebuilds them from this code. This hidden code is called the latent space. Now, this latent space is like a mysterious warehouse filled with boxes, and each box contains a blueprint for a different type of image, like dogs, cats, or zebras. The problem is, only the machine knows where each blueprint is. When we try to create new image using this magical machine, it's like blindly grabbing a random box from the warehouse. Sometimes we get lucky and find a blueprint for the image we want, but most of the time we end up with a box of nonsense, leading to a blurry or strange image. So, how do we fix the problem with regular autoencoders? Enter the variational autoencoder domain, or VAE for short. Imagine we put a fence around the useful parts of the latent space. This fenced in area is where we want our data to live. The VA's job is to figure out where to put the blueprints for things like dogs, cats, and giraffes inside this fence. Now, once the VAE has learned this, we can randomly pick a spot within the fence and ask the VAE to create an image based on this spot. Because the whole fence is filled with useful information, no matter what we pick or where we pick, we'll get a realistic image. That's the magic of VAs. VAs have a special ability. Points that are close together in the latent space creates similar images, which is important for generating coherent images from unencountered points in the latent space. That is, VA will perform well for those data on which it is not even trained on. This is useful when predicting signal strength in new parts of the warehouse. Now imagine the latent space as a map. If you are standing at one spot and see a picture of a dog, taking a small step in any direction will still show you a picture of something dog-like. Now this is super important because it means we can explore new areas of the map and still get meaningful images. Regular autoencoders couldn't do this. Example, if 100,900 is encoded to reconstruct a dog image, then 100.5, 900.7 will also reconstruct a similar image that is of a dog. To show a better comparison between autoencoder and VAE latent space, now autoencoder learns a hidden representation of the input, but VAE also learns to generate new data along with learning the hidden representation of the data. Autoencoder cannot generate new data, but VAs can. Autoencoder will not generate a shirt if the input is slightly deviated from the encoder vector, but VAs are trained to generate input with slight deviations in the testing vector. Talking about optimization, autoencoder aims to only reconstruct the input data by minimizing the reconstruction loss, and variational autoencoder aim to generate new images by minimizing the reconstruction loss and latent distribution loss, that is KL loss. In a variational autoencoder, each image is mapped to a unique multivariate normal distribution in the latent space. The mean vector defines the central point for encoding, while the standard deviation controls how much the encoding can deviate from that point. For each input data, for example an image, the encoder maps it to this mean vector. This mean vector represents the central point of the distribution for that specific input in the latent space. Therefore, each input image has its own distribution characterized by its own mean and standard deviation. The standard deviation is also a vector in the latent space and defines the spread or width of the distribution around its corresponding mean in each latent distribution. Generalization of these multiple univariate normal distributions gives us multivariate normal distribution. A multivariate normal distribution describes the probability distribution of multiple mutually independent random variables all having normal distribution at once. A multivariate normal distribution captures the correlation between these multiple variables. Let x1, x2 to xk be k mutually independent random variables all having a normal distribution, having mean as mu1, mu2 to mu and their variance as sigma square. And so the PDF of this joint distribution will be fx of x. A multivariate normal distribution is shaped like a multidimensional bell curve. The center of the distribution is determined by a mean vector. A multivariate normal distribution can be visualized as a multidimensional cloud of points with the mean vector representing its center. The central point is crucial as it indicates the representative point of each input image within the latent space. The spread of this cloud in different directions is determined by the standard deviation, which varies across dimensions. Mathematically, an multivariate normal distribution is an extension of the one-dimensional normal distribution into higher dimensions. Its defining characteristics is that each dimension is independent and follows the standard normal distribution with a mean of 0 and a variance of 1. This specific configuration is what distinguishes a standard multivariate normal distribution from other multivariate normal distributions. This is what helps us in constraining the latent space in variational autoencoder and removing any unwanted area as can be seen in the autoencoder latent space model. For example, considering a bivariate normal distribution with parameters mean and sigma, its PDF can be seen as this. For an image dataset, the mean vector is the point in latent space or multi-dimensional space. For each input image or input data, the encoder maps it to this mean vector. This mean vector represents the central point of the distribution for that specific input in the latent space. The standard deviation is also a vector in the latent space and defines the spread or width of the distribution around the mean. Therefore, each input image has its own distribution characterized by its own mean and standard deviation in a VAE framework. Mean, mu, a vector indicating the central point for each input image in the latent space, and the standard deviation vector, a vector that defines how spread out the distribution is around its corresponding mean in each latent space. Therefore, for a MNIST dataset, the latent space might look something like this, and for each random input, the VA will output some kind of image of the digits. To keep this distribution close to a standard normal distribution, we use the KL divergence loss function. This helps ensure that the mean and variance of the training data distribution latent space align with the standard normal distribution. The latent space vector is calculated as z, which is mean plus sigma into epsilon, where epsilon is the standard normal distribution. The encoder generates the mean and standard deviation for each latent variable and then samples from this distribution to create a latent vector, which is passed to the decoder to reconstruct the input. Instead of directly outputting the vectors in the latent space, the VA's encoder outputs parameters of a predefined distribution for each input. The VA then imposes a constraint on this distribution, making it a normal distribution to regularize the latent space. In a VAE, the encoder outputs the parameter of a probability distribution, typically a Gaussian, from which latent variables are sampled. However, this sampling process introduces a non-differentiable operation, that is, it's difficult to determine the curve of the sample latent distribution, thus making it challenging to backpropagate gradients during training. A non-differentiable operation is a mathematical function or process that does not have a derivative at one or more points in its domain. This means it's not smooth and continuous, and its rate of change cannot be defined at those specific points. In machine learning, especially in gradient-based optimization algorithms like backpropagation, differentiability is crucial. These algorithms rely on calculating gradients to update the model parameters and minimize the loss function. If a function is non-differentiable, these algorithms cannot be applied directly. The reparameterization trick addresses this issue by introducing a deterministic transformation that separates the random sampling from the learned parameters. This allows gradients to flow through the model during backpropagation. The reparameterization trick is a technique used in VAEs to make the sampling process differentiable, like a Gaussian distribution. Reparameterization trick, a technique to backpropagate through the sampling process in the latent space. Instead of directly sampling from z mean and z log variance, we use the reparameterization trick. We start by sampling epsilon from a standard normal distribution with mean 0 and variance 1. We then adjust epsilon to have a desired mean and variance, that is z equal to z mean plus z log variance into epsilon. This reparameterization trick keeps all randomness within epsilon, ensuring deterministic gradients, that is, it enables gradients to flow backward through the layer during training. By keeping all the randomness within the variable epsilon, the partial derivative of the layer's output remains deterministic, that is not dependent on the random epsilon. Deterministic gradients are vital for backpropagation through the layer and training the neural network efficiently. KL divergence. It measures the difference between two probability distributions. And evidence lower bound elbow. The objective function optimized during training, combining reconstruction loss and KL divergence. So the problem is, if we want to train a VA network model, we have to generate samples and then using backpropagation gradient descent, we need to differentiate that to tune our encoder and decoder parameters. If z is computed randomly, then backpropagation will not be able to compute an estimate of the derivative. Therefore, we use the reparameterization trick. The reparameterization trick relies on the fact that we can use a basic univariate normal distribution to make the backpropagation process possible. The loss function is defined by the VAE objective. VAE has two objectives. First one is reconstruct the input and second one is latent space should be normally distributed. Here in reconstruction loss, that is an exception operator because we are sampling from a distribution. KL divergence measures the distribution between two probability distributions. By minimizing the KL divergence, we are fine-tuning the probability distribution parameters mean and sigma to closely match those of the distribution or the target distribution. The VA aims to minimize the KL or Kullback-Leibler divergence between the approximate posterior distribution learned by the encoder and the true posterior distribution. This is combined with the reconstruction loss to ensure the generated data is similar to the original input.